Hey everybody, I'm Chili. Welcome back to Intermediate C++. This is part 2 of tutorial 2 where we're talking about pointers, and this video picks up where part 1 left off. Now I'm going to be teaching you about some less frequently used but still important pointer operations, const correctness with pointers, pointers to pointers, C++ style casts, and just a general motivation for why we want to learn and use pointers. Now in the last video, we learned a lot of pointer shit. So now we got a whole bunch of things we can do with relation to pointers. We can dereference a pointer, we can get the address of a variable so that we can store that in a pointer, and we can index from a pointer. And there's actually a whole bunch of other bullshit that we can do with pointers, and we call this stuff together, we call it pointer arithmetic. So let's take a look at what this stuff is. So one thing we can do is we can increment a pointer. Let's take a look at how that works. We're going to set our pointer to point to the first element, element 0. We're going to set that element to 99. Now we're going to increment the pointer. Look at the pointer value, D4. When we increment it, D8. And you might say incrementing, that only adds 1. But with a pointer, incrementing means move one int over. And an int is 4 bytes, so it adds 4 to the address. And now if we store 88 into what's pointed to at by the pointer, where do you think it'll go? Element 1 in the array. And similarly, we can decrement, and that is going to move the pointer in the other direction. So again, store 99. Let me just go back to the array here. We store 99. We store 88 here. Now if we decrement the pointer, store 77, it's going to go back into element 0. We can also do plus and equals with an integer on a pointer. And well, what do you think that's going to do? Well, again, we assign P is going to be element 0. We assign to P. Then we add 2 to the pointer. Look at the address, A0. Now A8, right? 2 times 4 is 8. The size of an integer is 4. So it's moving it over by 2 integers. And then if we assign 88, 88 goes into here. And again, the same works for minus and equals. You can also add and subtract without assigning, and that will return a new pointer. It won't modify this pointer, but it'll return a new pointer that is that pointer, plus 1. And then you could dereference that and set it to some value. And that's actually the same as just indexing into the pointer. So add 1 and then dereference is the same as index. As you can see here, element 1 gets set to 55, and then it gets set to 44. All right, 2 more kinds of pointer arithmetic. One of them is you can compare pointers with each other. You can use all the different comparison operators with your pointers, and here's an example of why you might want to do that. So let's take a look again at our sum function. Same deal, only this time we're going to do it using a different kind of pointer arithmetic. So what we're going to have 2 pointers. One pointer, P, is going to point to the element that we're currently working with, and another pointer, E, is going to point to the end of the array. And what we're going to do is we're going to keep moving P over until it reaches E, and every iteration we're going to, add up the sum. So the idea here, at the beginning of our function, P is going to point to the beginning of the array, E is going to point to the element, the space in memory after the last element. And this is important. So we calculate E by doing P plus 3, which will give a pointer to here. And then for every iteration of the array, we access this one, we add it to the sum, and then we move P over by 1, like this, and then we add that in, and then we move P over by 1. Every time we compare it with E, is P still less than E? Okay, then add, and then move over. And now we compare, is P less than E? And no, it's not less than, so we quit out of the loop, and we return the sum. So you can see here, we step into the function, and now we initialize S to 0. We initialize E to be P plus the size, which is 3. So now E is going to be this plus 3 times 4, which is FeO4. And then we just keep dereferencing P and adding that to S. So we dereference P, there's a 1. Now we increment P we make P point to the next thing. Now it's pointing to the second thing in the array, and we compare with E. Is it still less than E? Yes, it is. So we do the thing. We increment, we compare. Is it still less than? We do the thing. We increment and compare, and now it is not less than, now it is equal to E, so we exit out of the for loop and we return the calculated sum. So that is how you can use the pointer comparison. And it's not just less than, you got greater than, less than or equals to, not equals. All those comparisons can be done between two pointers as long as they're of the same type. Now, the last operation is you can subtract one pointer from the other. And what that does is that gets you the distance between the pointer in elements. So you subtract two pointers and you get the return value of an int. So let's say you got a situation like this. You got pointers P1 and P2. P1 is made to point to element 0. P2 is made to point to element 3. If you subtract P2 minus P1, the result is going to be 3 because it is 3 elements away. So it's not the difference of the raw address numbers. That difference between these addresses is 12. It's the difference in terms of the size of the type. So the distance is 3 ints. So P1 is 3 ints away from P2. And that, my friends, is all the pointer arithmetic bullshit. As you can see, most of these things either return a pointer or they evaluate to a reference to a variable that you can, mess around with, except for the comparison, which returns a bool, obviously, and the distance or the subtraction between pointers, which returns an integer. Now, if you want Chili's advice, I say stay away from a lot of this pointer arithmetic bullshit as much as possible. They make pointers even easier to fuck up. Index is used a lot, and obviously dereferencing and getting the address of, but all this other stuff, we don't use it so much. Now, I will be using them a little bit in the next few tutorials, mainly because A, we need to get in a little practice, and B, this pointer arithmetic is actually a very important concept because it's very close to something called an iterator, and iterators are used a lot in the standard library. They form the backbone of a big part of the standard library. So understanding this pointer arithmetic will help you to understand iterators. Alright, now let's talk about everyone's favorite topic. And when I mean everyone, I mostly mean me. And that is const correctness. So, pointers are variables. So like other variables, you can have constant pointers. But there are two ways of constantness that you can have for a pointer. It's a little complicated, but it makes sense once you think about it. So, let me just show you by giving you an example. We've got this int pointer here, pointer to int. If I make it a constant int pointer, what this means is that this pointer cannot be used to modify the thing it points to. Take a look at this sum function. All it's doing is it's reading values from the array, but it's not changing the array in any way. So the smart money is to make this pointer a const pointer, that way enforcing the contract that we will not be modifying that array. And if we compile this, it should compile fine, and it does. But if we were to try to do something like, let's say, let's go p at 0 is equal to 69. Now the compiler is going to be pissed off. It's going to say expression must be a modifiable L value, which in English means you can't modify this. You can't modify this shit. Why? Well, because you made the pointer const, dummy. So don't do this shit. So that is one way of consting a pointer. The other way of consting a pointer is if you put the const between the star and the p here, that means something else. What that means is that you can't retarget this pointer. You have to set it up. So it's like consting any other variable. You can't change the value, the address stored in the pointer once it's initialized. So, and again, this will work fine because we're not changing what p points to. We're indexing off of it, but we're not changing p itself. But if we tried to do something like, let's say, p++, again, the compiler is going to say, must be a modifiable L value. Get the fuck out of here with that shit. And again, we're not in this function, we're not retargeting p. So it would make sense to make this const, but I generally don't, the same reason as I generally don't put const here, even though I should. Maybe. It wouldn't be a bad idea. Most people don't, as far as I've seen. They don't usually make const their parameters to their functions like this. But most people, most good programmers, do make their pointers const in the sense that if it doesn't modify the thing that's being passed in, they say const int pointer. This is very common. You see this all the time. And well, obviously, if you've been watching my beginner series, you've seen with references, that's what I do with references, right? If I'm passing something in by reference, it's not being modified, it's const reference, always. So same thing with pointers. So to recap, const before means you can't modify the target. Const after means you can't retarget the pointer. All right, now another thing you might be wondering about is, okay, so pointers point to variables, right? But a pointer is a kind of variable. So can a pointer point to a pointer? And the answer is yes. You have to declare it the correct type though. Just like anything, if I want a pointer to point to something, so let's say I want a pointer to point to a pointer to int, I do pointer to int. Just have 2 stars here, and we'll call it pp, and it is equal to the address of p, and that works fine. If I tried to put the address of a in here, the compiler would not like it, because this thing is supposed to point to a pointer to int, and this is the address of an int. We want the address of a pointer to int, so we gotta put in here p, and then everything is okay. Now I can use this to control the pointer. So for example, I can do star pp is equal to the address of b, and then if I go star p is equal to, let's say, 111, we're going to run this. It starts to get confusing when you've got pointers to pointers, but we'll see what happens here. So we set p to point to a. So far, so good. Now we set pp to point to p. Now we use pp to retarget p to b. So now p should be targeting b. So now if we access the target of p, we should be accessing b. So b should change to 111. And it does change to 111. Now we can go one step further, because we can use pp to access p, but we can use p to access whatever p is pointing to, which will be, at this point, it's a, right? So we could use pp to access a. All we gotta do is dereference pp. That will give us p. Then if we dereference p, that will give us a. So if I set this equal to, 999, this should set a equal to 999. Let's try it out. So initialize, set p to point to a, set pp to point to p. Then we're going to double dereference pp and set that to 999. And there we see that a has been set to 999. And this can continue. You can have pointers to pointers to pointers, but don't do that. There's a joke on the internet called, a 3-star programmer. If you're using 3 stars on your pointers, you're doing it wrong, bro. Generally, you want to avoid even the 2 stars. It makes things more complicated to reason about the more indirection you have. And I know there's going to be a small percent of you looking at this and you're going to be like, oh, this is some cool shit. I can't wait to use this. Just don't. You're going to make me facepalm so hard. All the experienced programmers in the room are just going to lose absolutely all respect for you. So you want to avoid these as much as possible, but they do come up every now and then, and they might come up in the tutorials, I don't know. But I just wanted to make you aware of the fact that you can have pointers to pointers and you can dereference them like this. Now, you remember I told you, if you create an int pointer to int, it can only point to ints, right? If I try to store the address of a float in an int pointer, the compiler is going to complain. And that is true, but you can get around this. And the way you do it is called a reinterpret cast. So you go reinterpret cast, and then I can go, so I want to reinterpret this to an int pointer from a float pointer. And you do this, and the compiler says, okay, dude, you got it. Now we're going to treat this like it's an int pointer. So now this pointer to int is actually pointing to the bytes of a float. And then you can do something like I is equal to dereference of P, and I'll store that in those bytes into I. And we can see what the bytes of a float look like when you interpret them as an int. So if we step into this, step over this, step over here. So this is what the floating point number 420 looks like as an integer. It's, it's big integer, looks kind of random. Can't really see the pattern in there, but that's the way it is. They're completely different representations, so they have completely different values when you reinterpret them. So yeah, you can reinterpret shit, but here's the thing. Don't do it. You can do it, but don't do it. In general, it works. But as far as the standard goes, it's undefined behavior. It depends on the platform. So this is called type punning, by the way. When you view the memory at one location as a different type, it's not considered good practice, and I don't recommend you do it. There are rules for the things you can reinterpret and the things you can't, and they're kind of complicated. But I'm going to give you the only rule that you need to know, and that is you can interpret anything you want as a car pointer. So this is fine. You can reinterpret anything as basically an array of cars. So I could reinterpret this float as an array of 4 cars and then copy those cars somewhere else. That is the only, for our intents and purposes, that is the only type of reinterpretation that will be allowed. Now, some of you might be asking, can't we use our good old friend, the parentheses cast, like car pointer, this? Can we do this? And the answer is yes, you can. There's nothing wrong with this. This is called a C style cast. This is called a C++ style cast. And the difference is the C style cast can do any kind of casting. It has unlimited casting power. The C++ style cast is limited, so this kind of casting is only used basically for casting pointers, reinterpreting pointers. And there are other kinds of casting. And you might say, well, Chili, why? Let's take a look here. So here are the 4 kinds of C++ style cast. We got reinterpret casting, and the other main kind is static cast. Static cast can do things like convert a float to an int or that sort of shit. And you might be asking, well, Chili, so why aren't you using the C++ style cast to cast from float to int? And the reason is, well, let's take a look at it. So which of these do you prefer? Which one do you think gives you less eye cancer? I generally prefer this one. Because, look at it. This is just too much fucking typing for a simple conversion from float to int. So while it is more correct, I'm not going to argue, it's more correct to use this kind of casting. And I use this kind of casting for more complicated cases. For simple cases of conversion, for example, between float and int, I just say, fuck it, just use this cast because it's so much shorter. Ain't nobody got fucking time for this bullshit. So this is my philosophy, and that's what I'm going to be using throughout the series. For very simple conversions, just use C style. And for more complex conversions, use the C++ style, reinterpret. Or later on, I will show you static cast when we get into polymorphism and inheritance. And we might look at dynamic cast. I will probably never touch const cast because I don't ever have a use for it. But yeah, when I'm reinterpreting pointers, I recommend using the reinterpret cast. It's a narrower cast, and it makes it easier. If you use these casts like static cast and reinterpret cast, it also makes it easier to search your source code to find places where things are being cast. It's another advantage of the C++ style. So yeah, that's how you reinterpret pointers. And again, the general rule that I'm going to give you, the only rule we're going to worry about is only reinterpret to car pointer. Never reinterpret to anything else. If you follow that rule, you can't go wrong. For more details about this bullshit, you can Google strict aliasing. That's the name of the concept that governs the actual detailed rules of this casting bullshit. Now, to wrap things up, like I promised, let me just tell you a couple of reasons why you need pointers. Because like I said, you should prefer references whenever you can, but sometimes you need to use pointers. So one of the reasons why, well, generally, the reason why you would need to use a pointer is because you need to retarget something. So what's the case where you need to retarget? Well, there's a data structure, and it's called a linked list, and it basically composed of objects, and those objects contain some payload data, and they contain a link pointer, and the link pointer points to another object in the list. So you got one object, and that has some payload, and then it has a pointer, and that points to the next object with some more payload, and then a pointer to the next one. And the last object in the list, its pointer points to nothing. Now already here, you can see that this wouldn't work with references, because in references, you can't have a reference that references nothing. It's a bad situation. But with pointers, it's fine. You just set the pointer to null pointer, and that means that it doesn't point to anything. In the terms of a linked list, null pointer means this is the end of the list. And then when you want to do an operation, like let's say inserting an object into the list, you've got to retarget the pointer. So in this situation here, you've got an object that's object 1, you got object 3 and object 4. Object 1 is pointing to object 3, 3 points to 4. You want to insert object 2 between 1 and 3. So you've got to retarget this pointer from 3 to 2. And then you target 2's pointer to 3. And now the chain of pointers is like this. And you got a proper list of 1, 2, 3, 4. Again, this retargeting could not do that with a reference. Now, there's another situation where you're going to be using pointers, and that's where you're forced to. So let's say you're using a library like Box2D. Box2D likes to give you shit as pointers. So when you, for example, when you create a body in the world, a dynamic body or whatever, it will return to you a pointer to that body that you can use to do operations on the body. So you're going to need a pointer to store that, and you're going to access it through the pointer. And because that's the way the library is written, that's the way you got to do it. Technically, you could do this with references, but for whatever reason, the people who wrote Box2D decided to make it with pointers. And so you've got to use pointers. You got no choice. That's it for pointers. These two videos have been kind of a big information dump. Usually what we do is we have some game, right? And I say, let's add a feature to this game. And in order to add that new feature, I've got to introduce to you a new C++ topic, a new concept. But that wasn't really feasible for pointers. It's much better for me this time to front load the information to you. What is a pointer? How does it work? And then later on, I'm going to be giving you examples of how we actually use them in real applications, like for example, strings. My advice to you is that before moving on, you should spend some time playing around with pointers, just fucking around and experimenting with random shit. Also, review the list of topics covered on the wiki for tutorial 2 and make sure you have at least a decent idea of them before moving on. You guys, you're in intermediate now, so you gotta own this shit. Take a little responsibility for your own education here. In the coming tutorials, I'm gonna show you more practical examples of pointers, and I'm gonna give you more homework, etc. And in the slightly more distant future, when you're ready, I'm going to be showing you guys modern C++ techniques that make pointers safer to work with / more difficult to fuck up. But you got to take some initiative and practice this shit on your own as well. Now for the homework, I got 2 tasks for you. Number 1 is to take the sum function and make it use pointer arithmetic. Now I know I already showed you most of that in this video, but you should try it yourself and it'll be a good warm-up. Part 2 is a little trickier. I want you to write a new function that will reverse the elements in an array. And you should use pointer arithmetic for this bullshit as well. That's it for today. Thanks for watching. I hope you enjoyed my bullshit. If you did, do Chili a solid and smash that like button. And I will see you soon with some more C++.